In a previous video, we have gone over how you plot UV-Vis spectrum using Gauss view. What we would like to do now is to learn how to analyze UV-Vis transitions to learn from which states they originate or what are the whole states and into which states the transitions go, what are the particle states. In order to do that, we have to look into the Gaussian log file. So what I'm going to do now, I will go to the results, view edit output file. That will open the Gaussian output file. Next, I will search. So I will go to edit, find, and I will search for excitation energies and I will find them. So what I'm looking for is the line that says excitation energies and oscillator strengths. Okay, so it's down below here. Oops, and this is not looking so good. Let me see if I can refresh the screen. Okay, so now I can see it. These are excitation energies and oscillator strengths. What I am interested in specifically is excited state 1 and excited state 2. So what kind of information I have here? So I have excited state 1. It's telling me that this is a singlet transition. Next, the output file shows the excitation energy in electron volts as well as the excitation energy in nanometers. The oscillator strength of the transition, so in this case the oscillator strength is 0, so this is a so-called forbidden transition. And it also shows me the orbital from which the transition originates, which is orbital number 48 on the left of the arrow, and the orbital into which the transition goes, which is the orbital 49. So you can see that orbital 48 is the HOMO or highest occupied molecular orbital of the system, and orbital 49 is the LUMO, which is the lowest unoccupied molecular orbital of the system. The coefficient that's beside this whole particle pair, it's telling me the contribution of this whole particle pair to the excitation. The way these numbers are normalized is that sum of the squares of these numbers is equal to 1/2. So if you actually square 0.70463, this is going to be very close to 100%. Why is this important? Well, as you can see, some of the transitions, such as excited state 3, are composed of two different whole particle pairs. So for example, in this case, the excitation of one pair originates from orbital number 45, goes to orbital number 49, which is our LUMO, and this is its contribution. And there is contribution from a second pair, which is orbital 47, going to orbital 51, and this is its contribution. Okay, so if you want to get the contribution of the second pair, you take the square of minus 0.14675 and divide that by 0.5. So that's going to give you the contribution. Now, what I really want to do is to display the character of these orbitals, right? I need to display these orbitals to understand how these transitions look like. In order to do that, you need to open the checkpoint file, which I have done, and you need to generate the orbitals. So to get this orbital picture that I have already prepared, you do the right click, go to the tools, MOs, and then highlight appropriate MOs and visualize them. So what do I see here? If I look at the excited state 1, I can see that my electron is leaving orbital 48, which is the HOMO, which I have displayed here. Now, what kind of orbital is this? You can see that this mainly corresponds to the lone pair orbitals on the nitrogen atom. So this is a so-called non-bonding orbital or n orbital. So that's the whole. Where is the particle? The particle is orbital number 49 that I'm going to display, and this is a pi star orbital. You can see this is a pi system, and this is actually an anti-bonding orbital with respect to nitrogen-nitrogen bond. So this excited state 1 is a so-called N to pi star transition. How about excited state 2? Well, excited state 2 originates from orbital 47 going to orbital 49. So I display orbital 47, and this is a pi orbital. Okay, so this is a pi system, and this is actually a pi bonding orbital with respect to nitrogen-nitrogen bond. So this transition will be characterized as pi to pi star transition.